In this lecture, we will learn about how to find out the time complexity of some of the recursive algorithms. Let's say we are discussing about this factorial. Fine. The last lecture, in the previous lectures, we have discussed about this factorial, how to find the factorial. And the factorial can be found like factorial n is equals to n into factorial n minus 1. And if the value of n is 0, it will return 1 directly. We have designed a program also for the factorial. This is the program for the factorial recursively. Sorry, this one. This is the factor program of the factorial. And we have seen that on every function call, we are storing the activation record in the stack region. Now suppose we have to find out the factorial of 5. If you see the activation records, then in the activation record, first we have stored the activation record of 5, then above this factorial 4, above this factorial 3, above this factorial 2, above this factorial 1, and above this factorial 0. Then you can see that we are at any point of time, all these are pending. Fine. So the maximum, at max, how many activation records are pending? 1, 2, 3, 4, 5, 6. So you're finding the factorial of 5 and 6 activation records are pending at maximum at any point of time. If we consider that, it is just an assumption that activation record is taking a constant space. Let's say the space taken by an activation record is C, and which is a constant. So in this case, 6 into C space is reserved in the stack region. So this is actually an overhead, and space is encountered. We are actually consuming this much space. So we'll say that this is actually causing the space complexity for us. Fine. This much extra space is required for the execution of factorial function. So now if we are finding the factorial of n, then n plus 1 space is reserved on the stack region in the form of the activation record. So we can say that n plus 1 into C, because we are considering that for every activation record a constant space is required. So n plus 1 into C, this much space is required in the memory. So that we can say that theta n space is required. So the space complexity of factorial function recursively is theta n. And this space is just because of storing these many activation records. Fine. And what will be the time complexity? You see that every time a function is called, you need to check this condition. So if n is 0, you will return 1, otherwise you will call this function. So either you will be doing this or you will be doing this. Fine. So if you are doing this, then in this case the activation records are maintained. Okay, so doing the push and the pop operations on the stack is required. Fine, doing push and the pop operation in stack is required. So if you're doing the push operation, let's consider this as one operation. So n plus 1 times you need to push the records or the activation records, and n plus 1 times you need to pop these activation records. So n plus 1 plus n plus 1, it means this is 2 into n plus 1 operations are required, push pop operations are required. Now if you say that push and the pop operations require, let's say, the constant time, then in that case the total time required is 2 into n plus 1 into, let's say, a constant c dash. Now 2 is a constant, c dash is a constant, 1 is a constant. In that case you can say that it is actually consuming theta n time. Fine. So theta n time is required and theta n space is required for this algorithm. So you can see that for the recursive function we can find out the time and space complexity like this. Let's take another example. Suppose we have to find a raised to the power b. Let's say we have to find a raised to the power 5. For finding a raised to the power 5, you need to first store the activation record of a raised to the power 5, and then above this you will store the activation record of a raised to the power 4, above this a raised to the power 3, above this a square, above this a power 1, and then finally the activation record of a power 0. The base condition has reached. Now you can store the activation record of a raised to the power 0 at the first, and you can return the value from here. So these are the activation records. Fine. Now you can simply see that for finding out the a raised to the power 5, you are actually storing 6 activation records. 6 activation records are pending at any moment. So the space complexity may be because of this. Okay, so space complexity of this algorithm is also b plus 1 into constant space, let's say c. Let's say every activation record is taking a constant space. We can say that it's not b, it's n, so it will be a better way to write n plus 1 into c. Instead of writing this a power b, I'm taking it a power n. So n plus 1 into c is the space required. In the notations you can represent it like theta n. Why theta n? Because this is actually, this much is required. In any case it is required. There is no best case, there is no worst case, there is only one case. These many activation records will be pending. Okay, and since you are finding out this a raised to the power b, these many push and pop operations are also required. So 6 push operations and 6 pop operations are required. 6 times you will push the activation record on the stack, and 6 times you will pop the activation records from the stack. So n plus 1 times you need to push the stack, and n plus 1 times you will pop the stack. So 2 into n plus 1 operations are required, and every time you're performing the push and pop, we are assuming that this push and pop operations are constant time. So c dash. So the space required here will be theta. Sorry, time required here will be theta, and 2 is a constant, 1 is a constant, and c dash is a constant. So we are writing the time complexity as theta n. Right. So number of pending activation records are telling us how much space complexity will be there, and how many times we have pushed the stack activation records, and how many times we have popped the activation records are telling us this is actually helping us to find out the time complexity of the algorithm. Now we have taken another example of computing the Fibonacci number, and if you have this one, let's say this finding out the nth Fibonacci number in the Fibonacci series, and in this we more than one recursive function is called Fibonacci n minus 1 and n minus 2. Let's first write the algorithm for the same, or the program for the same, function for the same. So let's say Fibonacci integer n. Here it will be returning an integer value. If the value of n is 1, it means we are finding out the first term. It will return first term directly as 0. It is a base condition. Otherwise, if n is 2, this is also a base condition, will return 1 here. Otherwise, means it is neither 1 nor 2, then we will return Fibonacci n minus 1 plus Fibonacci n minus 2. Right? So this is the function for recursive function for finding the nth Fibonacci term. Now let's say we're taking an example of finding out the fifth Fibonacci term. So finding out the fifth Fibonacci term means f5. f5 can be found by calling f4 and f3, and then f4 can be found by calling f3 and f2, and f3 can be found by calling f2 and f1. f3 can be called by calling a function f2 and f1. Fine. Suppose we're finding f6. So we'll first find f5 and then f4. We have already have the resolution of this f5. Let's expand this f4. This will be f3 and f2. Then calling this f2 by f2 F1. So wherever this F2 and F1 is coming means that we have the base conditions and the value of n is 2 or 1. Fine. Now just to find out that how many times the activation record was pushed on the stack and how many times it was popped, or how many pending activation records are there, let's first compute that how many pending activation records are there. Okay, because the number of times we have pushed or popped will be different from number of times, number of pending activation records in this case. So suppose we have to find out fifth activation record, fifth Fibonacci term. So sorry, sixth Fibonacci term, for example. So F6 is called, it is pending, and we will call F5 and F4. So first F5 is called, F4 will be pending. So F5 is called, and then from F5, F4, this F4 is called, this will be pending. Then this F3 will be called, this will be pending. This F2 is called, and you can directly return this value of F2. Fine. Once you return the value of F2, this activation record will be popped. And then you can call this F1. So this space is free. Activation of F1, activation record of F1 can be formed at this place only, at the same place where F2 was. So now F1 is also will be returning a value, it will be returning the value to F3. So once we have the value of F3, this F3 can be popped. And then we will call F2. So activation record of F2 will be called, or will be made here only. Then this F2 can return the value directly, so this will be popped. And then I have the value of F3 and F2, so F4 will also be complete, so we can pop this. Then I can call this F3. In the same place where F4 was, F4 has been popped out, so obviously above this F3 activation record will be called. So for F3 it is F2 plus F1, so first F2 is called, activation record of F2. F2 can return the value directly, so it can be popped out. Then F1 is called. And then F1 can directly return the value, so it is popped out. F3's value we have found by adding these two. F3 can be popped. Then I have the value of F4 and F3, so F5 I have. So F5 can also be popped out. It can return the value now. Fine. So for F6, this part I was actually covered. We are covering this part now, F4. So on the activation record, you can see that we only have this F6. So above this F4 is called. For F4, F3 is called. For F3, this F2 is called. F2 can return the value directly, so it is popped out. And F1 is called. It can also return the value directly, so it is also popped out. We can now have the value of F3. F3's value is there, so we can pop this one also. And then F2 is called. We now have direct value of F2. It can also be popped out. We now have a value of F4. It can be popped out. So we now have the value of F5 and F4 both. So F6 value is also there. So the activation record of F6 can also be popped out. If you see that the maximum activation records which are pending are 1, 2, 3, 4, 5. At any moment, the maximum activation records which are pending are 5. So if you are finding out the factorial of 6, 5 activation records are pending, and if you are finding out the F9, not Fibonacci, nth Fibonacci term, then n minus 1 activation records will be pending at any moment. So you can say that the space complexity is theta n. But we cannot say the same for the time complexity. Time complexity depends on how many times we have pushed the activation record on the stack and how many times we have popped from the stack. So let's try to find out. For finding out the same, in this tree, in this arrangement of the tree, just consider that we are removing these two parts from here and we are adding these two parts here. Okay? So just for the assumption that we have this part is removed from here, these two parts, and the same two parts are added here. Fine. Let's say this is x and this is y. This was x and this is y. So these two parts are added here. Now we do not have this part. So these are actually representing the function calls. Every time we are making a function call, an activation record will be pushed on the stack. And every time a function is returning a value, that is actually popped out from the stack. So this is not there, and we have the tree like this. If this is a tree, let's say this is level 0, this is level 1, this is level 2, and this is level 3. Now see how many nodes are there at level 0? Only one. How many nodes are there at level 1? 2. How many nodes are there at level 2? These are 4. And at level 3 we have 8 nodes. Right? So it can be written as 1 plus 2 power 1, 2 square, and 2 cube. We were finding out the 6th Fibonacci term, and the last term here is 2 raised to the power 3. So can it be written as 2 raised to the power n minus 3 for if you are finding out the nth Fibonacci number? Obviously, if it is fn, it will be 2 raised to the power n minus 3. So for the bigger number, for finding out the bigger number in the Fibonacci series, a bigger tree will be formed. So if the value of n is 6, then we are finding out up to 8 or 2 raised to the power 3. If it is n, it will be up to n minus 3. So this is the total number of recursive calls. Now you see that this is an arithmetic, this is a geometric progression with a common ratio 2. And the number of terms here is n minus 2. If you remove this one, number of terms are n minus 3. If you include this one, the number of terms will be n minus 2. So the sum of this will be a into common ratio raised to the power number of terms minus 1 upon common ratio okay. So this is a into 2 raised to the power n minus 1 upon common ratio. So this will be 2 minus 1 n minus 1. Okay. So this is 2 raised to the power n minus 2. So this is the total number of function calls. And how many times push operation will be performed? 2 raised to the power n minus 2. And every time this value will be popped out, we will be performing the pop operations. It means that those many times pop operations are also called. So this is the push operation and this is the pop operation. So total number of operations performed are 2 into 2 raised to the power n minus 2. It means 2 raised to the power n minus 1 operations. Now if you are performing these many operations, and if you consider that every push and pop operations requires constant time, so 2 raised to the power n minus 1 into c, you can say that the time complexity of this function is theta 2 raised to the power n. C is a constant, 1 is a constant. We'll omit all these things while writing this one. And theta 2 raised to the power n is the time complexity of this algorithm. And you say that this 2 raised to the power n is a very large quantity, very huge quantity. Okay, if you take just a simple example to understand how big this quantity is. Let's say n is 10. So for n is 10, 2 raised to the power n minus 1 means 2 raised to the power 9. Fine. 2 raised to the power 9 is actually 512. So 512 activation records will be pushed and 512 activation records will be popped. It's a big quantity. Okay. Now so let's say n is 20. So let's say we are not finding 2 raised to n minus 1, we are finding 2 raised to the power n. Approximately that will be equal to that only. So it's just easy to find. 2 raised to the power 20. 2 raised to the power 20 is actually 1024 into 1024. This approximately equals to n lakh. So 10 lakh operations performed. Can you imagine? And similarly, let's say n's value is 30. So it will be 2 raised to the power 30. 1024 into 1024 into 1024. This is equals to 10 crore. So you see 10 crore operations are performed just for 30. So how big this operation is actually. So it is having a lot of overhead. It is performing, it is finding 30th Fibonacci term by calling the function 10 crore times or performing 10 crore operations. That is very big. And if you try to find out the Fibonacci term with the iterative function, not the recursive function, iterative function, it will require only 30 operations. It requires only 30 additions, or in even 28 additions, not 30 in fact. N minus 2 additions will be performed. So only 28 additions are required. So it is not necessary that the recursive functions will always result in the good time, or those recursive functions will always give us the answer in the good time. They may also prove to be very bad. What's happening here? In this case, it is a very bad algorithm. Okay, so if we say that this 2 raised to the power n minus 1, and this term can be said that this is the exponential complexity, and whenever there is exponential complexity for any of the algorithm, that is not acceptable. So the exponential complexity is never acceptable. Fine. Thank you.